Hey guys, so my name is Annika, and welcome to Chapter 12 of Holt Physics, which is sound. This chapter is going to be divided into three main sections. First, we'll look at sound waves. Second, we'll go over sound intensity and resonance, and finally, we'll move on to harmonics. So first of all, in this video, we're going to look at sound waves. The fundamental thing to keep in mind when we're looking at sound is that all sounds begin with vibrations. This is helpful because we looked at waves and vibrations in the previous chapter, which you can refer to if you need any help moving on through this chapter. So for example, we'll take a tuning fork. A tuning fork works when you hit it against something, causing the two prongs to vibrate, and it emits a noise. As the tuning fork vibrates, compression occurs when the prongs move closer to one another, and rarefaction occurs when the prongs move away. And they just go back and forth in a pattern of those two. So compression is defined as the region of the sound wave in which density and pressure are at a maximum, so that's when the waves are close, and rarefaction is the region of a wave in which density and pressure are at a minimum. And sound waves, we'll keep in mind, are longitudinal, so they can be modeled using a sine curve, just as we went over in Chapter 11. So now we're going to define a few characteristics of sound waves. The first is frequency. The frequency of a sound wave determines its pitch as perceived by the listener. So waves humans can hear are typically between about 20 Hz and 20,000 Hz. Any frequency below that is known as infrasonic, while frequencies above 20,000 Hz are called ultrasonic frequencies. And the pitch is defined as how high or low we perceive a sound to be. So that depends on frequency and also on other factors such as background noise that can affect how we listen to the things around us. And another thing to note is that while frequency is a set quantity or number, pitch is only a perception. So that revolves around exactly how people hear the sounds around them. A second characteristic of sound waves is their speed or velocity. This depends on the medium through which the waves are traveling. So we learned from the last chapter that the medium is the substance through which a wave moves, and that waves move at different speeds through different mediums. So, sound moves faster through solids because their particles can respond more rapidly to disturbances. As you can see, in a solid such as aluminum, the particles are much closer together, so they respond more quickly when a sound wave travels through. However, in air, the sound can't travel as quickly because the particles are more spaced out and they have a greater response time. So, to kind of put this in perspective, the speed of sound through air is 340 meters per second, while the speed of sound through aluminum is 5,100 meters per second. A final property of sound waves to keep in mind is that they're three-dimensional. So in the past, we've sort of looked at waves as being one-dimensional and traveling in only one direction. But in real life, sound waves travel in three dimensions as they move away from a vibrating source. So even though this shape is three-dimensional, that's impossible to draw. So we represent three-dimensional spheres of sound waves in two dimensions using a series of circles, as I've drawn below. In this case, the blue circles represent wave fronts, which are centers of compression within the sound waves. And in real life, each circle would be represented as a spherical area through which the sound is emanating. The distance between these wave fronts is the wavelength, or lambda, which we learned about in the previous chapter. And another term to keep in mind is rays. These are perpendicular lines that indicate the direction of wave motion through this diagram. So if the rays are pointing out this way, perpendicular to these wave fronts, that's the direction in which the sound waves are moving. Now, when you're listening to a sound coming from a moving object, for instance, a car or train moving past you, you've probably noticed from experience that as the car moves by you, the sound it emits seems to get lower and lower. We'll use the example of a train to demonstrate this effect. So relative motion of a vehicle moving by tends to change an observer's perception of the pitch. This is because as the train or car moves towards an observer, so towards point A as the red arrow indicates, the wave fronts reach the observer more often, making the wavelength shorter. This is because the train is constantly moving, so it's emitting wave fronts with shorter wavelengths in front of it. However, the velocity of the sound is always the same. So if we've defined velocity as wavelength, or lambda, times frequency, and the wavelength is decreasing, then in order for velocity to stay the same, frequency must increase. That's what makes the sound higher when the train is moving towards point A, to an observer, again, the observer is standing at point A. Now, once the train has moved past the observer, so now the observer is effectively at point B, the wave fronts reach the observer less often, making the wavelength longer and the frequency shorter, therefore the sounds are lower. This phenomenon is known as the Doppler effect, which is defined as an observed change in frequency when there is relative motion between an observer and a source of sound. In this case, the observer is fixed at either point A or point B, but the train is moving by, creating relative motion.